So today we are going to explore one of the best techniques that is out there for both classification and regression analysis. Tree-based models are fantastic models that can do a lot of things, and it involves stratifying or segmenting the whole space into some subspaces that each represent a category that share same characteristics, or each represent um, an absolute value that represents the whole region. So this is called decision trees method. So let's work with some some very interesting topics in decision trees. So let's assume. So I am sure most of you are familiar with decision trees, and maybe in some other courses of yours where you put a condition here, and based on this condition you decide whether you have to go this way or this way. If the condition holds, you usually turn left. If the condition doesn't hold, you go right. And then you have some other conditions here. Let's say x2 more or equal to 5. If the condition holds, you come this way. If the condition doesn't hold, you come this way. So yeah, so the idea of finding decision trees here is almost the same thing, with the difference that we have to find where to divide our subspaces to different ones. So in this very simple example, we are, if I call this space x1 and this space this vector x2, we are trying to find a region like something like this that separates our space into three different subspaces. So each of these end nodes are considered as a region. Each one represents one of these regions. So tree-based methods are extremely easy to interpret. So these are one of the best tools that you have for interpretation. The problem is when it comes to predictability, as much as they're interpretable, they don't do that much of a good job in prediction on their own. However, if we enhance it and we use some more advanced techniques like bagging, boosting, and random forests, we will see that while we use multiple trees, let's say forests of trees instead of just one tree, we can improve the prediction significantly. And that's the power of more amazing techniques that are there for trees. So to wrap up, if you're just working on one tree, it's extremely interpretable, it's not predictable. If your goal is to find predictability, then we have to grow a lot of trees and consider them simultaneously. And that's where we lose interpretability, but we significantly improve our predictability. So trees can be used for both interpretation and prediction. Depends what the context we're trying to use them. And the great thing about them is we can be used for both regressions and classifications simultaneously. So it doesn't matter if you're using it for quantitative outcomes or classifications, you can use it. And the other great thing about it is that for classification problems, if you have more than 2 outcomes, it still can do a pretty darn good job. So let's work on an example here. Here we have the baseball player's income on salary, and their salary is shown on the spectrum from dark blue to green and to red. So the closer you're to blue spectrum, the lower you earn. The more sexy color you have, red or yellow, that means you're earning more. So green is slightly more than blue, but less than red and yellow. So here we have the information on the years that they played versus the number of hits each player had during the last year. I want to see how that affected that. So just by visually inspecting this scatter plot or yeah, we can call it scatter plot. But just visually looking at this plot, what we can see is that before 5 years, or perhaps 4.5 years of experience before this line. Oh, it's not a straight line. Sorry, I have to try to draw a straight line. Okay, so let's call this a straight line. Please accept that as a straight line from me. I'm using a very interesting pad that that is not that precise. So before this straight line, what we can see is that no matter how many heats you had, your income would be small. But after this line, let's say if you have 5 or 10 years of experience, then what determines your income is more number of hits. So we can say we can split this space furthermore and say, okay, oh, this looks like a good straight line now. Okay, we can say that, okay, before 5 years of experience, it doesn't matter how much heat you had, your income is low. After that, it depends how much you do. If you are among the people who hit a lot, you earn a lot. Otherwise, you earn moderately. So visually, we could see what is happening here. But how about we grow a tree and see what are the underlying mathematics behind them, and see how we can find these regions mathematically. So if I want to show that, show the same tree that we explored, we found that if you have less than 4.5 years of experience, your income is low. I explained a bit what this 5.11 is. If your years of experience is more than 450, that means you do not satisfy this condition. You're earning more. You come this way. And if you come this way, you see, okay, it depends on how many hits you had. If you had significant amount of hits, your income would be this much. And if you have less amount of hit, your income is this much. So what you see here is your income in log. So this is 10 to the power of 6. That means 1 million. This is 10 to the power of 6.74, which is a value closer to 78 million. And this is 10 to the power of 511, which is a value around 200K. So what we observe here is that on average, the people who had less than 4.5 years of experience earning around 200K. If you have more than 4.5 years of experience, the number of hits is less than 117.5, you earn around 1 million. If you have a lot of experience and also a very good hitter, you earn around 7 million. So for this hitters data, oh, by the way, there's one more point I wanted to make, and that is, whenever you draw a tree, we have several branches here. So we have end nodes. These guys are called terminal nodes or end nodes. Each one represents one region. So we had, if you can remember from this, we had 3 regions. Let me call it region 1, region 2, and region 3. So these 3 regions are represented by these nodes. This represents R1, this represents R2, and this one is R3. So these are called end nodes. At the same time, or terminal nodes. At the same time, we have other nodes here, which are not terminal nodes. These are called intermediate nodes, your internal nodes. So these are internal nodes. These are terminal nodes. And usually, when you wanna show a tree, what you need to do is show the length of the tree, and that should correspond to the value that variable has in dividing it. So here we can say years of experience is a more important factor in defining your wage than number of hits you have, because the length of the branch you have here is way more than this one. So we try to show the hitters data on on a scale of log, and that was why 6 represented a million. We saw that at a given internal nodes where we had 2 internal nodes, years of experience and heaters, the left-hand side represents whenever the condition holds. The right-hand side represents whenever it doesn't hold. So we have a condition at any internal node. And at last we have terminal nodes, and at each terminal node we have the average of the outcomes of that region, and that's our prediction for that special region. So how many regions did we have? 3. How many terminal nodes did we have? 3. So in this case, we have these beautiful 3 nodes, and our predictions for each region would be the average of all observations in this region. So if you want to predict any point in this region, you report the average of all incomes you observe in this very region. You do the same thing in this region and that region. So as you can see, as you can perhaps remember, the average of this was around 200K, this one was around 1 million, and that was around 7 million. So again, whatever we said earlier is repeated here. We have 3 regions, and each region is considered as a terminal node. The trees we grow are upside down. So this would be a more beautiful tree if we would grow it this way, but it's not easy to follow that if we do it this way. Let's work on gravity and put the tree upside down. We can interpret it better if we do it this way. So the trees we grow are upside down, and we have some internal nodes. Whenever you sub-branch, you have an internal node. So we have an internal node here and also an internal node here. So what we learned in our tree was that years of experience was the most important factor. Why? Because the length of the tree was the largest. Given that a player has less experience, given that a player had more experience, the number of hits was an important factor. So that was the better understanding of that tree. That's the summary of what we got from our tree. But the question is, how do we build these trees? What is the best way of building these trees, and how did we find 3 regions? Why not 4 regions or 5 regions or 10 regions? So let's use a little bit of math to formally define what we are going to do, and later we see why it's complicated to solve the trees directly, and that's why we use some greedy approach. So first we should decide how many distinct regions we want to have, or how many terminal nodes we want to have, J. In the previous example, we decided to have only 3 terminal nodes. You can have more and more and more. Then you have a feature space. These are the variables you had. In the example before, we only wanted to find your income. You wanted to predict the income of heaters based on 2 variables. And the variables, if you can remember, was years of experience and also number of hits. So here X, we have only 2 X's. So we have number of features here, we only had 2. That's why it was a 2-dimensional shape. And number of terminal nodes we want to have. In that case, that was 3. For every observation that falls in the region that we define, we make the same prediction, and our prediction is simply the average of all values in that region. So if you want to formally define the best tree that defines the whole thing, what we need to do is try to minimize the difference of our observations, these are our observations, and our predictions. So how you do that is say, okay, we have 3 regions. Within each region, we only consider those observations that are in those regions. That's what this notation is for this summation. And for each observation, we make the prediction that is the average of all observations in that region. We just want to minimize the whole thing. So the way that we minimize that is by defining these subregions. So we minimize by considering these subregions. And if we can minimize that, anytime we make a new subregion, what we will have is simply will give us simply the predictions as well. So finding these subregions is equivalent to finding these predicted values, because you're dividing your space, and as I said earlier, within each space, within this subspace, your prediction will be everything that is inside it. So ideally, we want to find these regions such that it minimizes the whole space. Unfortunately, this minimization problem is extremely hard to achieve. It's NP hard, and NP hard problems can easily be exhausted since the amount of computation you need will improve exponentially there. So unfortunately, there is no known algorithm that can solve it directly and give you the optimal level. So unfortunately, we're stuck there. That's why we use a greedy approach. So let me explain what greedy approach is in maximization problem, because that's a very important distinction. So let's say you have three variables here. You can get into three paths from the beginning. So at the first stage, you need to decide whether you want to take path A, B, or C. Let me see if I can change the color here. Hopefully I can do that. Okay. It seems like it's better that I don't. Okay. So I stick to the same color. Sorry for that. And let's say in the second step. Oh, okay. I think I need to. Okay, something bad happened to that, and it jacked. Okay. Oh, okay. It seems like I can change the color on part of the monitor that you cannot see. Okay, and that weird sound comes from there. Okay, we have blue here. So let's say at the second step, for each of our decisions, we have also three decisions. Let me call it A2, B2, C2, and we have the same thing for B. Let's say we have this, which is A2, B2, and let's call it C2. And then we have this one, which is C1, C3, B3, and let's say this is, oh, I'm sorry, and A3. Okay, it's better that I do it backward. Okay, A3. So if you want to get the longest jump by deciding where we want to end up from the beginning, the best path we can get is from B, then A2. That we will end up here, right? That's the amount of improvement we get. So that's the most. That is the tallest jump we can get. If we jump B first, then A2. That is the furthest we can go. However, if it's not possible for us, if we are short-sighted and we only focus on the first couple of observations, we only focus on what we can do on each stage, then the best thing we can do in first stage, not considering what will happen later, will be to take this route, this path, and then this path. So we will end up here. And that is called the greedy approach. In greedy approach, you do a greedy thing. That means each time you only want to maximize what is best right now without considering what will happen. That's why it's short-sighted. You may end up into the optimal solution, but usually it's not guaranteed. So here, if we want to do a greedy approach, we first take the path A, because A is the tallest or the most extreme leap that we can get from A, B, and C. That's the most improvement that we can see. But and in the second stage, when we are here, we take leap B, and so we end up here. But as we can see, that is not the best optimized or most efficient way to go. If we would take the step B first and then A2, we would end up to the optimal solution. And that would be when we would consider all the leaps. And by the way, if we would take C and then A3, we would get into a better place than what we got from our greedy approach. But at least our greedy approach is better than some of our outcomes. So it's always best to look forward, but unfortunately, as you can see, if we just move from these steps further and further away, the number of branches we have to consider, if we want to consider, let's say, 10 steps ahead, will increase exponentially. And there will be a point that we cannot do it anymore. But unfortunately, as we saw here, that is not possible to look over all possible outcomes, and that's why we work on a greedy approach. In a greedy approach or top-down approach, what we are trying to do is at each point, on each step, we are trying to find the value that for now decreases the error as much as possible. So let me explain it in the next slide. So let's say we have this space. Let's say we have different variables here. So in the greedy approach, what we do is that both vertically and horizontally, we are going to divide our subspace into many subspaces. So for example, we start from here. We call this R1, this called R2. We make a prediction and say, okay, R1 prediction is the average of whatever we have here. R2 prediction will be here. Then we estimate one error that is for this way of splitting our data. So let me call it error 1. Then we split our space with a parallel line. So we get a new R1. Let me call it R11 and R21. Again, so the prediction for this space would be some prediction, the average of all observations here, and the prediction will be here. So we get E2 to that. So we do it up to the time we shift our line down up to the time we touch the bottom part. Let's say we get En. We repeat our division by vertical lines now. So we get this division, this division, this division, this division, and this division, go to N. And we get, each time we do that, we get, let's say, E'1, E'2 up to, E'2 up to E'N. Then we see within all the vertical splits that we had, and from all horizontal splits that we had and all vertical ones, which one has minimized the error? So let's say E2 was the one that minimized the error. So in first step, we say, okay, what I know now is that E2 is fixed. So this line is fixed. So in the second step, so in the first greedy way of splitting this, so this line would be our first split. In the next step, within its subspace, we again go over all potential horizontal splits and vertical ones. Same here, horizontal splits and vertical ones. And then with each split, we found which one caused the least amount of error. And let's say in the next step, this is the split we get. That should be a horizontal line, a vertical line, by the way, a straight vertical. So next step would be we consider all horizontal and vertical splits within the subspace, all vertical and horizontal splits within the subspace, and all horizontal vertical splits within the subspace. And let's say we get this one, and the next step we get this one, next step we get this one, this one, this one, and so on and so forth. So we just, each time we take the horizontal or vertical subspace dividing point that minimizes the whole error, total error. So by the way, that was just the definition of how we would split our space into two-dimensional shape. If we had a three-dimensional shape, I couldn't show it, so that's why I just stick to the case that we have two variables. So let's get back. Oh, by the way, one thing to mention that here, we could continue splitting the space at our will. We could split it even more and more and more, and we would define more and more and more subregions. So how do we decide where to stop? It's slightly complicated, but we're going to explain that. So for now, accepted from it for fixed amount of subregions, which comes from the terminal nodes that you fixed, parameter j in our previous slide. You can divide your subspace this way with a greedy approach, and that was the greedy approach. So we first select the predictors, how many predictors we want to have. Then we started subdividing our subspace such that we minimize the residual sum square by that division. Remember that when you divide your subspace, your prediction for that subspace would be the average outcomes you get from that subspace. The average outcome you get from that subspace. So the best one would be the one that creates the least amount of residual sum square, which is the summation of all observations from your predictions squared. So you do that over and over again until the time you get a good split. And that good split is the one that minimizes the RCS within all of your choices. You do it over and over again until the time you get to the number of regions you want. So what is our predictions? So we predict response for given test observations. So as always, you can just divide your data set into training and test observations to see how good you're doing, because it's very easy to overfit the data, specifically if you divide your data such that you're only left with one observation in this subspace. Your training error would be exactly zero, because in each subspace you have only one observation. Your prediction for that will be that very observation. So your prediction for that subspace would be 100%, for that training set would be 100%. However, that may clearly be an overfit. So in next slide, what we see is what are the subspaces that we can create and what are the ones that we cannot. So unfortunately in decision trees, this way of splitting the space is not possible. We can only divide our subspaces into rectangular shapes, and that is what is possible. So this shape is possible, and that represents this tree. This shape is not possible at all. And this shape is a three-dimensional representation of the same tree. This vector z, represents the outcomes, your prediction outcomes. x1 and x2 are the same feature space that you have here. If you look over this three-dimensional shape here from above, from here, I accepted from it, this is your eye. If you accept it from me and you watch it from this direction, what you will see is exactly this tree and exactly this region. So you can exactly see this region. This would be R1, this would be R2, this is R3, This is R5, and this is R4. So your prediction for each one is the height of this. So R1 has the lowest Z. Let's say your prediction for that is 0. This one has slightly better prediction. Your prediction for that is slightly more. Prediction for R3 is slightly more, and so on and so forth. So the things we learned is that this shape is not possible because it's not contain all rectangular shapes. This is a non-rectangular shape in between. And everything else is pretty much described. So stop here. I stop the course here. We are going to continue the course with another notion, pruning the trees. So thank you for now. I see you in a couple of in my next video.